than many others, as we have the possibility to use calibrated instrumentation, which I will show you in a moment. But our independent quantification mode has advantage that can serve for validation purposes. So let's see. For the introduction, just to recall the topic, and you're all very familiar with this, I took a picture from the spectroscopy article, and I'd like to put emphasis a little bit on what we actually do when we talk about TXRF analysis. TXRF analysis is a physical technique using, for example, monochromatized X-rays to excite a minute amount of substance on a flat surface and probe the element-specific fluorescence radiation, or to be more precise, the intensity of the element-specific fluorescence radiation by means of an energy dispersive detector. So typical angles for the critical angle of total reflection or external total reflection are in the hard X-ray range about 0.1 degree. In soft X-ray range, they can go up to 3 degree, and I will show you one of, let's say, the programmatic slides regarding works in the soft X-ray range, because you can distinguish the effects more clearly. You all know the different angular responses for surface contamination, layer type depositions. And the leading form of our calibration scheme is a chemical traceability scheme. That means that you use well-known single or multi-element solutions. So you know what you have in, you know how much of this element is in the solution, and use it in form of a dried droplet sample, either for pre-calibration, so when you probe the efficiency of the detector, or when you follow the concept of an internal standard, where you compare a known amount of the internal standard to the unknown analyte. I'd like to briefly show you the motivation that we had at PDB to address this field. I'm more from XRF than from TXRF, or grazing-incidence XRF, which some of you may notice in the way how I argue. And like to briefly reflect some of the standardization ventures of the last 20 years and try to contribute to, let's say, the clarification of terms that we are having in X-ray spectrometry under grazing incidence, which includes, of course, TXRF in the range, in the angular range below the critical angle of total reflection. So key motivation for us, or a starting point for us, TXRF was analytical challenges related to nanotechnology. You have dozens of new nano-scaled materials that appear every month. Technology R&D cycles are down to 3 or 4 months, and this requires, on the R&D level, but also on the quality level, the correlation of the material properties with the functionality. Functionality, either efficiency or degradation of efficiency when dealing with aging. And this means that we have changing requirements on the sensitivity, discrimination capability, and information depth. So for most analytical methodologies, this, one has to rely here on reference materials or calibration standards, but there are only few at the nanoscale. And this is one of the interesting points for TXRF. They cannot get a well-defined and stable contamination layer of a thickness of 0.1 nanometer. So what we are doing complementary to this chemical traceability chain. So chemical traceability means you refer to certified reference materials. are calibration standards that are qualified by traceable methods, is that we deal with instrumentation that we use. So we calibrate the unknown instrumental parameters, efficiencies of the instrument, and then use knowledge on interaction cross-sections to do the quantification. This is a website that I'd like to recommend to you of the Federal Institute of Material Testing and Research in Germany, which collected information on an international level about the nano-scaled reference materials that exist. And if you have a close look, for example, on the film thickness, this is about half of the number of reference materials that exist. And this expresses very nicely, or demonstrates very nicely, the analytical challenge, because the reliability of analytical results depends on the similarity of the sample that you like to analyze as compared to the reference materials, or to be more precise, the spatial distribution, spatial and compositional distribution of the matrix elements within a reference material. So I started my talk saying that there are about dozens of new materials every month popping up, and we have only 2 dozens of thin film reference materials. And this is the reason why we decided to address this increasing gap between the existing number of nano-scaled reference materials and the new materials being introduced into the market. And this includes also surface contamination to be dealt with by TXRF and other techniques. I'd like to very briefly summarize how we do this. We use synchrotron radiation from an electron storage bin, and this synchrotron radiation is monochromatized by either means of crystal or grating monochromators. So we have well-known radiation and the soft and hard X-ray range, and well-known means that these beamlines are optimized with respect to spectral purity, which means that more than 99% of the radiation that we can guide to a sample has the photon energy that we would like it to have from the pre-selection. And on the detection side, we use two complementary principles. On the one hand side, we operate storage ring as a primary source standard, so you can calculate the radiation being emitted from a banding magnet with an uncertainty of about 0.1% to directly calibrate the efficiency of an energy dispersive detector. And one can calibrate photodiodes behind the monochromator by means of electrical substitution radiometer. That's basically a cavity cooled down to liquid helium. And when you allow monochromatic radiation to pass into the cavity, you just reduce the heating power to keep the temperature constant. And this can be done also with uncertainties in the 0.1% range. These two techniques we use to calibrate the detectors that we use for TXRF analysis. And here are the examples, for example, SILI or STD detector, where we can reveal directly the efficiency, and then we get the spectral responsivity of the photodiodes that we use to determine the incident flux or excitation intensity in TXRF analysis. This is how we work at PDB, and it's slightly different from what you have when working with a laboratory instrument. So in general, you do not know exactly the spectral distribution of an X-ray tube with respect to its radiant power or intensity and the spectral distribution itself. So for an X-ray tube, this is known with uncertainties of about 20%. Same holds on the detection side. You get some data sheet from the manufacturer and you get a good estimate of the efficiency of the detector, but you need to rely on, let's say, standard data, but not measurement data on the system that you actually use. And our key competence is to provide this information, all these instrumental parameters. And in addition, we can determine X-ray fundamental parameters by means of transmittance measurements. These are the data that you need to use, for example, by means of an XRF quantification using the Sherman equation. So here's an example of the determination of L-shell photoionization cross-sections. And you see a different energy dependence for L1 as against L2 and L3 subshell data. So these are the subshell photoionization cross-sections for molybdenum. And in particular for L1, the deviations can be as large as 300%. So when you rely here on databases that are often implemented in the instrument, as quoted by this jump ratio approximation that was recommended by UPAC until recently, as far as I know, you may add up with very relevant deviations if you use these wrong values for the quantification. In the upper left side, you see the way how we do a spectral deconvolution. So we use from the calibration of the detector the information on the spectral response of an energy dispersive detector, and then convolute the spectral response with all the emission lines of the element of interest, include the self-absorption correction, preferably obtained experimentally from thin layer transmittance measurements, and uses deconvolution based on each absorption shell for a physical model of the deconvolution. So it's not a mathematical model. And you see in the upper left side how well this works when comparing the fit as against the measured spectrum. Deviations that we still have there in the lower range are presumably due to the spectral background contributions that have not yet been modeled physically. So this is a very short survey of what can be done with TXRF and related measurement techniques. So traditionally, the energy, the incident photon energy, is the main operational parameter that is being changed in XRF analysis. And we have seen the requirement of tuning the analytical sensitivity or information depths by means of appropriate operational parameters with respect to the characterization of nano-scaled samples. So what's of interest is to use on a flat substrate the so-called X-ray standing wave field that is formed for the determination of contamination, a nanolayer, or a near surface either diffusion profile or implantation depth profile. We can probe nanoparticles or even near surface interfaces. All this can be done with laboratory instruments when you have synchrotron radiation with the capability to tune the incident photon energy. You can perform a speciation, for example, by means of X-ray absorption. Fine structure, in this case, one has to adapt the X-ray standing wave field to the structure. So when you change the incident photon energy, one has also to change the angle of incidence correspondingly to keep the integral intensity, field intensity constant, either in a nanolayer or an interface. This is a look in the instrumentation. Current instrumentation that PDB operates, basically a UHV instrument that allows for TXRF, grazing-incidence, and XRF regime. It allows to operate two detectors. You see the one in the synchrotron radiation in the storage ring plane from the right, excitation radiation coming in from the left side in yellow, and we have 6 translational, 3 rotational axes. We can perform XRF under grazing incidence, including the TXRF regime, in conjunction with X-ray reflectometry, which is a direct means to probe the X-ray standing wave field that we need for quantification TXRF or grazing incidence XRF. And we can include optics in the yellow excitation channel to go down to micrometer, even into the nanometer range. And there exist a few copies of these instruments for laboratory source at the Technical University Berlin, the French Metrology Institute at Soleil in Paris, and IAEA at the Italian storage ring Elettra in Trieste. This is the instrument that we used for TXRF characterization on 200, 300 millimeter wafers. And I like to start with this to indicate you how we perform the quantification in TXRF. You see here a TXRF spectrum of samples that are spin-coated wafers. Actually, there were nearly 100 of these wafers produced by an Italian semiconductor company, contaminated with transition metals in the level of 10 to the 12 atoms per square centimeter, and light elements like sodium and aluminum, 10 to the 13 atoms per square centimeter. And you see here, for the example of aluminum, the response function that we use. So it's a physical model of the detector, physical background contribution, like the resonant Raman, scattering part, and the deconvolution of the spectrum. When you know then the incident photon flux, detector efficiency, and solid angle, you can do a TXRF quantification without the need for one elemental or multi-elemental solutions that are right on a sample. And I don't want to go into the details of this equation, just to give you a flavor of the principles. This is a Sherman equation that is well known in X-ray fluorescence analysis. And there are basically 2 differences to standard XRF analysis. One is the modification of the excitation conditions by the X-ray standing wave field. And we have a different concept of the solid angle of detection, because this is actually a convolution of the incident beam footprint in conjunction with the angular acceptance that is associated with the detector. So I'd like to briefly show you the kind of quantities that are entering here. The master position means the mass associated with the determined number of atoms of one element divided by unit area, and this can be translated in this form into an expression, so a variation of the Sherman equation, that basically contains physical quantities such as the photon energy of the excitation radiation, the radiant power or intensity or flux of the incident radiation. Then, very important, the relative intensity of the X-ray standing wave field at the wafer surface, which is for contamination often a constant at the critical angle of external total reflection. We need to know the angle of incidence, the energy of the fluorescence radiation, the detection efficiency of the energy dispersive detector, and I will come back to this effective solid angle of detection, observation angle, and then a few so-called X-ray fundamental parameters or interaction cross-section that are either tabulated or we started to determine part of these values together with industry or within European projects to get a more reliable estimate of the values and related uncertainties. When you follow this approach, there's not much you need to do to transfer reliable quantification, for example, from silicon wafer to a different material. You just need to calculate the X-ray standing wave field. Everything else remains the same. And this implies that you need to know the optical constants for a new substrate material, which can be revealed, for example, by X-ray reflectometry. These are the uncertainties, or the uncertainty breakdown, the various contributions to the uncertainty of the analytical results that PDB claimed in the very first version of this ISO 17025 compatible quality management work item on TXRF analysis of the contamination on SE wafers. So, and the main contributors here are the knowledge on the X-ray fundamental parameters. So by reducing those values, moving from literature data to own data, one can bring down the overall uncertainty. So now I'd like to come to this concept that is frequently not completely understood. So you see to the upper left side an excitation beam profile. In our case, we have a beam with full width of half maximum, 140 microns times 40 to 140 microns. And when you allow this beam to illuminate, for example, contamination on the wafer, you end up with this beam footprint at 0.9 degree. This is in the soft X-ray range. In the hard X-ray range would be 0.1 degree, and this footprint would be even larger. And this is what it's all about, how to calculate this effective solid angle of detection. So when you carefully analyze the collimator and active area of your detector, you see that you have a region with, so region B was a very high solid angle contribution, and a region A, which is partially reduced due to shadowing effect. The only thing then you then need to do, having set up this geometric function, and you can get information on the excitation beam, for example, by means of a knife edge scan. They just need to perform an angular convolution, and you get this position-dependent contribution to the effective solid angle. And this function is important because whatever you put below the detector has a position-sensitive efficiency. So imagine that you put a small dried residuum at position 0. You have the maximum efficiency in this case. If you put the pattern of aerosols impacted, for example, by the cascade impactor, in a diameter that is lower than 4 millimeter, you're not affected. If the deposition pattern is larger, you have a reduced efficiency, but not necessarily a reduced quantification reliability, as long as you know the location of this deposition pattern and its orientation. Okay, so this is the main work that you need to do, and I would say that not necessarily users of TXRF instruments, but providers of instruments or those who build the instruments themselves could get access to this information. And there are also calibration schemes to provide information on this. As I was to report a little bit on standardization aspects, I'd like to refer here to this already 12 years old round-robin activity within the ANA project. This was referring to the wafer that I've already shown you. It's 10 to the 12 atoms of transition metals and 10 to the 13 atoms per square centimeter light elements. And you see here the comparison of 5 TXRF instruments at different positions of these wafers to the right, as compared to atomic absorption spectroscopy, ICP-MS, and TOF SIMS. And you notice deviations of about 1 order of magnitude, which is way too much. And the question for all analytical techniques is, what can be the reason for deviations of, let's say, 1 order of magnitude? In general, one may say that this depends on the reliability of the pre-calibration of the instrument, on the measurement procedure, and on the quantification procedure. But it can also depend on the sample morphology. So you have contribution from unknown instrumental response, which I would relate to the pre-calibration. Then the interaction of the sample morphology with this instrumental response and sensitivity, and to some extent to the modeling of this experiments. This is an experiment that I've shown to some of you already, which surprised us a little bit while we did this. We got a few nickel droplets. Once again, this is in the soft X-ray range. And we got nickel droplets provided by the analytical lab of a large German semiconductor manufacturer. And you see here the cross-section, the lateral position across those droplets as against the mass, the absolute mass in nanograms that we had at the various positions. And we had in blue 1 nanogram, 10 in red 10 nanogram, black 100 nanogram. And when you do then at the maximum position, so close to the lateral position of 0, for all 3, this curves from the left side an angular scan. So basically, for the blue one, it's about 0.1. nanogram. For the red one, it's about 1 nanogram, and for the black one, about 4 nanogram that's in the beam. You see a different angular response. And this is due to the fact that the increasing mass of the element is modifying the X-ray standing wave field, and this is a key issue in a reliable TXRF quantification. Over the last couple of months, we tried to summarize those aspects for the German standardization organization DIN, and we intend to forward the suggestions towards the ISO TC21 SC10, which is on XRR and XRF, regarding grazing incident X-ray fluorescence analysis. And you see here 2 pictures, one to the left. It's basically the physicist's view. You see the 3 curves, the blue, the red, the black one that I've just shown you on the previous slide. And to the right, you see the chemist view on the same situation. I'd like to briefly explain you what's plotted there. So grazing incident XRF or XRF under grazing incident means you're doing X-ray fluorescence analysis at a shallow angle of incidence, and you may want to vary the angle of incidence or keep it constant, like in the case of TXRF. You see here to the left side 4 dots that correspond to total reflection XRF, modifications of the excitation conditions. And in addition, we introduced a green curve, which is just called angular resolved XRF. And the difference between, let's say there's some confusion about how to use the terms, also across the literature, also including our own group. So I think TXRF has a clear-cut definition. You have a flat substrate and hard X-ray range with roughness of 1 nanometer, soft X-ray 5 nanometer, and you are at an angle that is below the critical angle of total reflection. Grazing incident XRF goes above this angle by a factor of 3 or 4. Some authors may include the TXRF regime into this grazing incident XRF regime. The most characteristic feature of this angular profiles that are changing from the light blue to the red to the black is a modification of the X-ray standing wave field. So you have a modification of the penetration depths into the samples by the X-ray standing wave field. And this is different to a rough sample or a bulk type sample, where you have a modification of the penetration depths until a certain angle, when the penetration depth is replaced by the information depths regarding the angular profile of these techniques. And we got the impression that it's worthwhile to sort out these techniques also on a standardization level. And there are many advantages in extending the angular range beyond TXRF. One of them is, for example, that these techniques can serve for a validation of actually TXRF results at different angles. And for the sake of completeness, I'd like to briefly explain the chemist view, and I hope that the chemists among you will correct me if this is wrong. So one concept would be to create calibration curves for grazing incident XRF. By putting in a very defined way, for example, by a droplet deposition technique, an elemental mass on a substrate, and observing then the absolute fluorescence intensity. And the main difference between the TXRF, grazing-incidence XRF, and angular XRF is the dependence of the fluorescence intensity on the deposited mass. So in this TXRF regime, when you have a flat substrate as compared to a rough substrate, the increase in fluorescence intensity is about a factor of 2 faster than for this normal XRF regime. And this increase is slowing down from factor 2 slightly to a factor 1 with increasing mass, and all these curves meet in an XRF dependency. This is not a measurement, this is a conceptual view of how to sort out TXRF, grazing-incidence XRF, and an angular resolved or varying angle XRF at shallow incidence. What does it imply for the grazing-incident XRF regimes? When dealing with minute mass, and minute mass depends on the kind of substrate and the incident photon energy, and a flat substrate, we're having undisturbed X-ray standing wave field and optimal TXRF conditions. And when going above the angle of total reflection, we can see a very nice grazing-incidence XRF pattern with angular dependencies of the fluorescent signal that are modified by the X-ray standing wave field. And increasing the mass, we are having some sort of modified or degraded X-ray standing wave field, and we can still perform grazing-incidence XRF, but no longer total reflection XRF in the undisturbed regime. This is due to the calibration curve that I've just shown you. And for higher masses or rough substrates, the main difference is we no longer have an X-ray standing wave field, but we can reveal information by a variation of the angle, for example, about matrix elemental depth profiles. So for future standardization, this has 2 implications: that one need to determine the appropriate calibration samples for each of the 3 regimes A, B, C, and define corresponding calibration procedures. For TXRF, this has been done successfully, and this knowledge is available. And one has to determine the ranges of validity of these calibration procedures between these regimes A, B, and C. And I expect this to be work over the next 2 or 3 years, and we certainly will try to propose this kind of work from German side and include this in international round-robin activities. So to conclude my talk, I'd like to give you a brief flavor of round-robin activities. And Ola, you do me a favor and stop me when I exceed the time too much. So
you're fine.
Okay. So what I like a lot were the standardization, this TXRF standardization works in the semiconductor industry, because you have an ideal, you have a perfect flat substrate, and you have very minute amounts of contamination. So you are in the TXRF regime for sure. And so this round-robin activity, I think this was led by Ingrid Rink from NXP, showed reasonable agreement, adequate uncertainties. So I would all like to recommend you the Spectrochemica Akte Part B publication. There are other ones before 98 that are also rather good. What's interesting is, let's say, depending on the crystallization, and I think I learned this from Hagen-Stossnach, how important it is to have the same kind of salts regarding the spatial distribution of the various contaminants, and they have an impact on the angular response, even under perfect TXRF conditions, because you're getting a different kind of extra standing wave field. So one has to deconstruct layer and particle type surface contamination, which has been addressed 20 years ago in this round-robin activity. Then there were, which is very valuable, other more recent TXRF round-robin activities related, if I recall this correctly, to WAMAS, which is a pre-normative organization, to ISO. And this showed partially high deviations of results, partially reliable results. So this was worthwhile to reconsider. One of the attempts to reconsider this work has been performed by IAEA. I think it was 2016, 2017. I put a reference there, and this showed also this typical S-type diagram, but deviations that were, so maximum deviations that were rather high. And this was one of the reasons why we decided to do a round-robin activity that was financed from the German Ministry of Economy, but included an international participation from France and Japan on dedicated samples in 3 different classes. On the one hand side, the typical microliter droplets. Then, Ola, you know this pretty well, the nanoliter droplets that are formed from nanoliter dispenser. And coming back to the start of my talk, multi-elemental metal layers, so sub-monolayers that do not show any spatial distribution of the matrix elements. And this is now in print at yeah, it's already online if you like to get a copy of this paper. And this was a joint work together with Bruker Nano, with Meat, with the company AXO, and in the round-robin activities, Rigaku, Japan contributed, and the French Metrology Institute, LNHB, and PDB for reference-free quantification, and the University of Dortmund for consultation on the concepts. So, for example, one concept was, and I'm glad that Hagen is here, who may correct me, was a careful pre-selection of samples, so that with respect to the recovery rates, the samples were, so different types of samples were checked regarding their recovery rates. Those with the highest recovery rates were selected, and then individual samples were once again pre-selected to achieve a high uniformity of the spatial distribution of the depositions. This is how some of the samples look like if we have a look on them by micro-XF, so synchrotron radiation-based micro-XF, in order to provide the detection sensitivity that is needed. You see the typical ring-shaped residuum for the microliter deposition, the nice pattern for the nanoliter deposition, and the spectra for the submonolayer. And these are some results from this round robin and from the publication. You see here the weighted mean value for manganese and scandium, as well as the bar plots for those elements. So the interesting point was that the weighted mean values of all participants are in line with the nominal values with 5% uncertainty. This is what we were aiming at and what TXRF analysis can provide. So the performance of TXRF has been demonstrated. Similar results were obtained for nickel and yttrium, and also for the nanoliter droplets and for the thin film. We got similar values. So actually we had no big differences between the microliter droplets, nanoliter droplets, and thin films, presumably due to the careful pre-selection of samples. And here you see the box plots and median values for these measurements. Overall, one can state very good agreement. So a good agreement requires a reliable pre-calibration, a good knowledge on the instrument, an appropriate morphology of the samples to be analyzed. So the morphology of the samples actually determine the kind of physical measurement procedure that you are in. So you can measure at an angle of TXRF either in TXRF conditions or with a slightly higher mass grazing-incidence conditions, or with an even higher mass under angular resolved XRF conditions. And here's the same for nickel and yttrium. Of course, some values are outside, let's say, this band, but this is expected for a larger number of participants. And currently, we extended this in a second round robin activity to an even larger number of participants. So those are some of the current summaries. So we got, some may call it excellent results. Others may say this as results as expected. So with average incidence 5.7%, if I recall this correctly. So depending on the efforts that one spent, microliter droplets, nanoliter droplets, and thin films are all fine. Sorry, there's a typo. It's not milliliter, but microliter droplets, as on the previous slides. And the validation could be done. So PDB contributed here by physical traceable reference-free TXRF for validation purposes. The corresponding German norm or regulation has been updated based on these findings, and we're currently in the process of forwarding this information, the suggestion, to the international works. This is a slide that I got from collaborator Armin Groß, colleague of Hagen Stößner at Bruker Nano, regarding the TXRF norms. I have here one slide on the ISO TC21 that you get an idea which kind of countries are currently present here and what are, to give you a flavor of what have been discussed about 2 years ago regarding TXRF and related techniques. And I like to conclude my talk with 2 slides that one can use as reference-free approach that PDB has to qualify calibration samples. Here in the case of functionalized glass substrates, containing aminated monolayers, and we can just count the number of nitrogen atoms on the surfaces to provide calibration samples, for example, for XPS. And here's a second example of samples that are stable. This can be also used to create transfer calibration samples for TXRF analysis at other sites. And I will skip those slides on the aerosol application. I'd like to conclude my talk. Summary. So I've shown you some work on the reference-free analysis of contamination on silicon. I've introduced you to some of the standardization ventures in TXRF, shown you some specific aspects of recent round-robin activity, and introduced you to the requirements on TXRF calibration samples, such as lateral homogeneity and height. This was the implicated information in this recovery rate tests that we did. Introduced you to the concept of the effective solid angle of detection. And what I haven't shown you now to lack of time were this aerosol applications, but you find a web page here. And last but not least, I'd like to thank my team as well as all collaborators over the years that have enabled this kind of success and venture. And last but not least, I'd like to thank you for your kind attention.
Thank you. Thank you very much, Burkhard, for this highly interesting presentation. So let's first give you a great hand here. And it's always difficult online, but there's also the clap sign. And now I think we're ready to take questions.
Yep.
Okay, I have a question. So Burkhard, you have shown a beamline photo, maybe the first, second, or third slides of your talk. And in that slide, you show silicon lithium detector there. And also you are talking about SDD detector.
Mm-hmm.
Yes, this photo.
Yeah.
So my question is, are there any different usage or purpose of silicon lithium detector and SDD? And also other question is for the some standardization, which is better, you think, SDD or silicon lithium detector? So this is my question.
Thanks a lot. You're a very accurate observer. This is the old photo. So we started with silly detectors, and for the soft X-ray work, we had thin window silly detectors without supporting grid. So typical window thickness was 135 nanometer polyimide with a 20 nanometer aluminum oxide plus a 20 nanometer aluminum coating, and those windows cannot stand atmospheric pressure. So we had to keep those detectors in vacuum all the time, which was a pleasure for calibration work. But we needed the windows to prevent the detectors from getting an ice layer. And this is the main part of the answer to your question. The later SDD detectors achieved resolutions and peak to valley ratios and low tailing contributions like the SLI detectors after second or third technology range. I would say since about 7-8 years they are equivalent, and you can operate an SDD detector as a windowless detector and just allow to get it pumped down overnight in order to remove all kind of contamination or ice layer. The only thing, we still have one or two of them, and this is for the range 20 to 35 kV, for example, for geological applications. It's still interesting to have one or two of them. And our engineers, I hope they are not following, are unhappy that I'm still preserving one or two of them.
Okay, thank you.
You're welcome.
Laura Borghese raised her hand.
Ah, okay. Laura.
Okay, thank you. Thank you for this very interesting talk. I'm particularly interested in the slide where you show the chemist view. I appreciate that you touched this
you mean this one?
topic, because it's particularly helpful for people like me to understand. So my question is, if we in the lab we are not able to recognize the regime where we actually are from angular scan curves, and we have a response which appears like the one that you show on the right. What is your suggestion to proceed? How we can demonstrate the reliability of our quantification approach?
This is an excellent question, and it's not easy to answer. When we deal with one element, so Laura, I'm pretty convinced that one could create these calibration curves. And the question is then, do you know in which regime you are? So for example, if it's not possible through the droplets, one can certainly produce this through this sub-monolayer depositions. And I think one needs to solve this together with the manufacturers of the instruments. What I would expect, to give you a good answer, which is a little bit complicated, we take 2 or 3 elements and use cross calibrations depending on the absolute masses, so mixtures of the elements that different, let's say, elemental mass depositions are in different regimes, and then we should be able to determine this by means of angular scans. This could be one way, and this is exactly what we need to discuss a little bit. Usually what we do, if you have a look there on the left side, you can probe the absolute mass through the shape of the angular scale. But what are you doing when you have a TXRF instrument only? Then you need to know what are the threshold values. And the question is if you're dealing with one element only, you're on the right side. And then it's pretty clear. Or one element in, let's say, a well-defined matrix. But imagine that you have several matrix elements that may start to shift these angular scans. I don't know, perhaps some of the colleagues, in particular from industry, may like to comment on this. I have no easy answer for you right now without an angular scan. And perhaps, Laura, one possibility would be to prepare specific samples that you can compare with. But that's something that we need to develop altogether over the next 2 or 3 years.
Okay, thank you. Thank you very much.
Okay, let's see.
Hello,
Yes.
Can you hear? Can you hear?
Yes, yes.
Yeah, this is, thank you. First of all, thank you very much, Beckhoff, for the nice presentation. I have only one question. Suppose if I want to participate in this round robin test, what is the procedure?
You mean the one that we would like to start?
Yeah.
Pretty easy. You send me an email.
Okay.
Probably summer next year, or we will communicate this also to the ISO TC21 SC10. So, and we're doing this twice. So we were proposing this as an open, let's say, round robin activity as a German round robin with international activity, international participation. And then we do a round robin activity with a higher international participation. So you're more than welcome to join both of them. The first one was to find pitfalls of the samples. And then we were further reducing this also to have a reference. Let's say a reference document. And the question that Laura just asked is, these are the real challenges there between grazing-incidence XRF and angular resolved XRF. You're also very welcome to propose samples there. And I don't know if, as far as I recall, there are not many, let's say there are not many participants. Perhaps Laura can help me. Is this list of countries that are put on display for the ISO TC21 complete? Okay. Because this is also a way, so we had China and Japan from Asia, but for example, not India. And this might be another way to join these activities. This depends, of course, on the national standardization body in India.
Okay.
But
so,
please send me an email. It's not 100% sure that we get this together, but we are trying to organize this.
Yes, yes, so I will definitely send.
So second half of next year, hopefully.
Oh, thank you. Thank you very much.
You're very welcome.
Yes, maybe a question at this point. Maybe other people from the audience are wondering if they could join the round robin. Would you say that everyone who's interested should send you an email?
Yeah, for the grazing-incidence work, not now. We will start this, I would say 6 months prior to the TXRF conference. No, we will not be able to start it earlier than autumn next year. And then if you're interested, I think we will communicate this in this ISO committee. So where, for example, Laura and I are present, and where Bruker Nano is present, where Rigaku is present. And in addition, you can send me an email to find out. And we will organize this, have a look in this publication that I mentioned. We started with a small number of participants to identify threshold values, and then we are extending this. And the international round robins, of course, are very valuable for WAMAS or ISO related activities. But here we were to update as a starting point a German regulation and then propose it on international level. So we had to start with a German team. For the other one, we are in discussion. This is not yet determined. The slide that I've shown you is part of sorting out of this kind of activity. So when we think about how we may be able to address these regimes, yeah, in particular, I would be most interested regarding Laura's question if chemists could produce this kind of calibration curves.
I think that this could be quite easily done, because there are many chemists also among the network action members. So I think that it could be done. The main issue that we have is that if we provide this curve, we have to rely on the positioning of the sample inside the instrument, which with any instrument, commercial instrument available in the market, is not easy. Also, in the case of water, we have this issue with the instrument that we currently use in the lab, which is a box, and sometimes the repeatability of the same sample measured inside and outside or from the chamber is not as good as we can use for a calibration curve like this. But if there is a good repeatability, then we can produce such curves quite easily.
Yeah, this is very good to know, because actually what you may need is you take a flat substrate and you take the same flat substrate with a higher roughness. And then the one with the higher roughness should give the green curve, while the other one should give the blue curve, just to determine this. I don't know. It's a question of preparation, and it's a question of, let's say, availability of substrate. And once again, what we have here is in soft X-ray range, and I also hope that part of the validation work can be done in hard X-ray. Right. But I also think, Laura, this should be feasible, and this would require some chemist to check if our prediction is right.
So I think you said it, but what would be rough and what would be like smooth? So what would be the
rough? So for hard X-rays, the limit is 1 nanometer, more or less, and for soft X-rays, 5 nanometer.
Okay.
So better than 1 is smooth in the hard X-ray range. Now, because I think this might be one way of determining ways to identify where you are in this TXRF, grazing-incidence XRF, and just angular resolved XRF. And of course, one has to sort out the terms a little bit. We had some discussions here in Germany, and the terms used in different ways in literature at different groups. And I think it's worthwhile to sort this out in one way. And this is one suggestion. Others may come up with one. So we said, no X-ray standing wave field. This is X-ray fluorescence analysis. And for small angles, it's just angular resolved X-ray fluorescence analysis. And within X-ray standing wave fields is TXRF and grazing-incidence XRF. One proposal, but I don't know. Perhaps there are many competent colleagues in the audience. Perhaps some of them may comment on this. It's a suggestion when going to standardization. It's not a scientific argument, but I think one has to sort this out, as some of the works are going a little bit back and forth in a difficult way.
So are there more opinions on this topic?
Have you tried this? Because I feel that this is happening due to, sorry.
No,
Yeah.
please go ahead.
Yeah, so I feel that this is because of this nanoparticle formation, or this particle size basically affecting this profile of the GXRF. Do you think this is this possibility of this?
This is for particles below 200 nanometer. I expect this to be an additional effect, and one has to discriminate this. It's a very good comment. This was a simplification just by the mass. So it's a mixture of mass, increasing roughness, but you still have the excitation at the substrate. One has to sort this out, and one has to define samples for which this is of interest, and particles or even coarse particles is an additional class. So I would not expect to solve all the problems. I would expect some modulations when having nanoparticles, some modulations on the way, let's say, for the lower angular ranges. And the question is, that depends on the partner if one should include this. And it's not only aerosols. This might be also for other environmental applications where you have particles that one has to find a way to deal with monodisperse or polydisperse particles. And I think in the shape, this you can only see very monodispersed distribution of very small particles. This would be my expectation.
Yeah, you're right. So I feel that this is not monodispersed. I think this we have to take polydispersion, because we cannot take only one particle size. We should have a Gaussian distribution. We should take Gaussian distribution profile, and then we try to fit. And I feel that we'll find a solution. This is what I am expecting.
Yeah. Yeah, you're right. And for polydispersed particles, let's say all these oscillations disappear.
Yeah.
And yeah, at the time when we did this were dried residua. There were no particles involved and carefully prepared. This was the original semiconductor characterization process from one of the larger companies.
Okay. Okay, that we can, yeah, okay. I will think of what we can do and whatever I feel.
Yeah. And I know, Laura, can you briefly comment on how to join this? Is it possible for guests to join this ISO?
Round robin.
No, this ISO meeting, this SC10 meeting.
We have succeeded in inviting some extra experts to the meeting through the VAMAS network.
Okay.
If you remember, last year we did it, and we are planning to do also this year to invite Diane Eichert. I have to ask if it is possible to invite other experts as VAMAS expert, because actually there should be an indication from VAMAS of the participation of the person. In any case, I think that if there is an interest from the country of ARIAN, India should have the committee, its own member body represented in ISO. We can find a way to tell him who is the reference person for his country. And that would be also a positive thing, because ISO is looking for other countries to participate in the development of standard. And it would be an official way also for being part of the standard development.
Yeah, and Laura, an intermediate step might be to invite interested colleagues into this ENFORCE-TXRF Work Group 2 preparational meeting that you organize.
Yeah. Yes,
So,
yes. Actually, we can invite basically who we want in the meeting, in the virtual meeting of the cost action. So there are not usually many people that want to join such meeting, but in this case, if there are other people, they can freely contact me or you, and we can include them in the list of participants to join us in the meeting of the action. Meeting of action are not so formal like the one of ISO, so it is easier because we can simply invite them, send them the link, and they join. And of course they are invited also to join the action as action members, also from international partner countries. We usually ask, I think that Yasa usually ask, or Ursula usually ask the email of the people that join this TXRF Journal Club, because we include them in the dissemination list of the action to keep them informed about all the activities that they can join.
So the next opportunity for Aryan Tiwari to discuss with us would be then this preparational meeting and ENFORCE-TXRF Work Group 2, and Laura just sent a link for this. So if you contact us there, you're more than welcome to join the discussion. But I think the nanoparticles explicitly have not been a topic, but nano and micro. meter scale particles are in the discussion.
Okay, so I hope the information was helpful. So I think so. Are there more questions? I do not see more questions, and I think we already had a very good discussion. And my questions all were already answered, so I don't have anything more to ask. So before I close this session, I will give you some heads up for the next talk in September. That will be on Thursday, the 23rd, and it will be given by Dr. Kaushik Sanyal. He's from the Baba Atomic Research Center in Mumbai, India, and that will be at 4 p.m. Berlin time, CEST, and 7:30 p.m. IST. Okay, and I hope to see you all again then in September. And then let's thanks again to Burkhard for this very nice talk and great discussion. Thank you. And yeah, have a good day. Have a good weekend, I say already now. And see you again next month.
Thanks a lot, Ulla. See you all soon again.
Bye.
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 Bye, Martin.
Bye, Ulla.
Bye bye.
Bye, Laura.
Bye, Laura.